All right, so now we'll move on. We talked about one electron atoms, two electron atoms. We'll go ahead and jump rather than going three, then four. We'll talk about four electron atom, which would be the beryllium atom. The beryllium atom has a 1s orbital, which is the lower lying orbital that's there, and there's two electrons in it. And then the higher lying orbital, the 2s, and we've got electrons that are in that 2s orbital. A bunch of the terms that we've seen are going to be similar, but we've got one more term that we're going to add for a system like this. So first, we have our okay, we got two electrons in a 1s orbital. They have kinetic energy. We have two electrons in a 1s orbital. Both of those guys are attracted to the nucleus. Two electrons in a 2s orbital, they have kinetic energy. Two electrons in a 2s orbital, they have attraction to the nucleus. So we've seen all this before. What we're going to see next is similar to things that we've seen. I'll redraw it down here with this line, sort of line diagram. So up and down, up and down. Okay, 1s and 2s electrons. So what all have we got going on down here? A bunch of repulsions, J11, so it's a repulsion between this electron and that electron. So just like what we saw in helium, these two guys repel each other. Similar thing happens up top, J22, so this electron repels that electron. And then we got a few more. So this electron with both of those guys up top, so this one repelling those, we can call that J12. Okay, this top one going with those two, and then this bottom one repelling with those two. So we actually get four of those. So this one with both of them, and then this one with both of them. Anytime you want to count interactions between electrons, you can do it this way. So you can kind of draw them out. So my four electrons are there. This being my 2s, this being my 1s. I have my J11. I have my J22. And then I have my four J12s. So 1, 2, 3, 4. And so that's all of my interactions that I have for my four electrons. One with one, two with two, and then four times one with two. Okay, so this so far is not much more complicated, but there's one additional thing that actually ends up happening here. So for a system like this, we get an additional type of interaction. And this is, if you ever hear the term quantum weirdness, this is an example of quantum weirdness. We have, because it ends up that the up electrons, so the up electron with the up electron and the down electron with the down electron, they have an ability, they're very good at avoiding each other in space. And so we get two more interactions here. So this 1s up with this 2s up gets a term that's K, we call this K12. So this up with this up gets a K12, and then this down with this down gets a K12. All right, and don't blame me for this. This is not my fault, the weirdness of how we do signs with these things, but I'll point out to you guys then what happens here. So the 4-electron total energy, we don't have a nice equation here in terms of alpha, but I'm going to write out all these terms. So 2T11 plus 2V11 plus 2T22 plus 2V22. So this is always positive. This is always negative. This is always positive. This is always negative. The J's are always positive. So J12 plus 4J12 plus J11 plus J22. Okay, all of those, the total and all of them individually, are all positive. The K's are also positive, but when we do this, they get subtracted. Okay, and so the weirdness that I was alluding to is that for this term, we add a negative, which lowers the energy, and here we subtract a positive, and that also lowers the energy. And so everything that I'm going to circle here in green increases the energy of the system as that term gets bigger. Okay, as any of those terms get bigger, the energy goes up. And as any of these terms get bigger, the energy goes down. And so we don't have a simple calculation that we can do to show this to you in the way that we did for a 1-electron or 2-electron atom. But basically what ends up happening is these adjust their distance from the nucleus and from each other to overall give the lowest energy that we can possibly get. Beryllium atom is a stable atom, and so at the end of the day we get a negative value, but they adjust themselves to give us the most negative value they can. Okay, the electrons adjust in or out to get to that sweet spot where the energy is at a minimum. All right, one final thing that we need to talk about here. So if we have a system, for example, let's say the nitrogen atom, 1s, 2s, let's do the carbon atom, 2p, so 2s2, 1s2, 2s2, 2p, 2 we have here, and this is the ground state. Okay, and you've talked about this in general chemistry, you may have talked about it a bit if you've had it in physical chemistry. So this is the ground state compared to okay, that is not a ground state to have the two electrons paired up. That's because this repulsion, having them in, say, the x orbital together, is larger than having one in the x and one in the y. But what might not have made sense to you at the time, because you didn't have the requisite knowledge to figure it out at the time, was why this one would be worse. Okay, so this one versus this one. So this one here on the far left has a K, 2p. So this is an up electron with an up electron. We get a K from there. The K gets subtracted, so that lowers the total energy. Here, the J is probably about the same size because it's in, say, the px and the py, px and py. But the down, we do not get a K. no K value to get subtracted out. And so of these three, this would be the ground state, the lowest energy. This would be the middle, because they're at least in separate orbitals, so that the J between the two is not too bad. Here we have a bad situation all the way around. So they're both in the x orbital, so the J term between them is really big, and there's no exchange because one is up and one is down. Exchange interactions only happen in the case where we have electrons with the same spin. All right, and all of this is to say, so we talked about it earlier in chemistry as if we have some sort of magic that happens for half-filled shells, that they're somehow magical. So you have these special stabilities, is often how we talk about it, for something like when you have an electron configuration like this, or for the D metals, if you have an electron configuration that looks like this. This is a half-filled D, so this is a D5 system. This one here would be a P3 system. You talk about them as if there's some sort of magical quality for something being half-filled or totally filled. And what is behind this, and this is almost definitely a question that I'll end up asking you guys about, is those K interactions. So you get a ton of those exchange interactions, the Ks, which lower the energy. Those are referred to as exchange terms. And those guys are often called Coulomb terms. So the Miesler and Tarr text uses these. I'm using what you would use in a quantum chemistry or physical chemistry book. They actually use this uppercase pi for Coulomb and exchange. So if you want to look in the Miesler and Tarr book, this is how they're going to talk about that. But all of this is to just get us to the point to be able to understand the quote-unquote magic of the half-filled and the totally filled P and the half-filled and the totally filled D electron configuration. The homework for day 5 is given here. The helium atom is a 2-electron system. 2 excited states of the helium atom can be generated that have the electron configuration 1s1, 2s1. The singlet excited state has an up electron in the 1s orbital and a down electron in the 2s orbital, while the triplet excited state has an up electron in both the 1s and 2s orbitals. I'd like for you to write out the total energies of the singlet and triplet states using T's, V's, J's, and K's. After you've done so, use this to predict whether you think the singlet excited state or the triplet excited state of helium will be lower in energy.